many of you didn't start working on it at all, so it's not my fault if you think your time is tight. Okay, the log is there. Okay, so homework 5 will be due on Monday. Okay, maybe I will consider having it due on Wednesday, like 2 days after the phase 3 deadline. But then I will have to figure out a way for you to submit it. I'm still debating it, but I will not able to do quiz 5 in class. What I will do is quiz 5 online, so you can do it in your own pace, of course, with the time constraint, whatever, and check against the solution itself. Let me finish and ask questions. Then we will do the final test, I believe, on May 3rd. Is that right? Like I mentioned multiple times, I did not set up the time for the final test. The university does. We have a centralized scheduling system that dictates this. I have no control over that. So don't try to come to me and negotiate, oh, I need to take the final exam at this time, at that time, unless you have a really, really compelling reason. Then we should talk. Okay? Any question for that?
I was gonna say, like, can we do like a hand-in thing like we did for phase 2 with the homework?
For phase 3,
well, I mean, for the homework, if we're doing it on Wednesday, could we just do that and like submit like a PDF?
No, we are not going to print 140 submissions, right? For written homework, you have to print and submit. And if we're gonna do a Wednesday submission, what I will do is ask you to go to submit to one of the TAs. Okay? Yes, a little bit inconvenience for you. You have to come in physically, but keep in mind, so I'm not going to allow electronic submission for any written homeworks. Okay? Yes.
On Canvas, on the grading view, there's a built-in PDF viewer. You wouldn't have to print.
No, we're not. Like I said, we are not going to print electronic submissions. We are not going to do grading on electronic submissions. I know it might be more convenient for you, but it's a lot of work for us. And we have only 440 students. They're grading phase 2, phase 3. So a lot of work. Please show some understanding here. Okay, I appreciate it. Okay. Any other questions, comments you have? If not, then let's get started. So please keep in mind, I know some of you might say, oh, you have the, I don't want you to submit anything, honestly speaking. I don't want you to submit any projects. Because if you don't submit anything, there's no work for us. If you think it's a lot of work for you, think about how much work it is for us. I actually don't have to ask you to submit anything. Teaching, I enjoy my research. I don't have to create so much workload for me. I honestly don't have to do this. The only reason I'm doing this is for the benefit of you, trust me. I don't gain anything from giving you phase 2, phase 3, and homework 1 to 5. I don't get literally anything from this. Because the easiest for me is to have open book test, take home test for midterm and final, take home written homework, open-ended projects. Seriously, why don't we do that? Because I want you to learn, period. Okay? So keep this in mind when you think about, oh, I have to do this, I have to do that. If you tell me you don't want to do any of this, perfectly okay with me. I don't lose anything if you don't do anything, seriously. But at the end of the day, I feel I'm responsible to make sure you learn. Okay? That's the objective. Keep that in mind. Okay? All right, let's look at where we stopped last time. We talked about memory hierarchies. And here is a quick review of that. You have inside CPU, you also have main memory, and SSD, disk, and optimal storage and tapes. And cache and the memory are volatile memories, meaning that data inside those storage media will be lost if you lose power. And I posed a question to you last time, which is, so that's the thing I will appreciate you doing today, only for today. I really encourage question on that stuff. But because I'm really a little behind schedule, and this is one of the only 2 lectures left, I'm hoping that we can keep this class. Refrain from asking clarification type of question to my lecture, to my office hours. I would really appreciate that. But still, if you feel like there's something you really want to ask, go ahead. There's nothing wrong with doing that. I really encourage that, but only for today and the next lecture, because we're a little bit behind schedule. So keep that in mind. Now, so memory and cache are volatile because once you lose power, you lose data stored in memory and the cache forever. Okay? And in particular, last time I asked you why RAM, okay, which stands for random access memory. So why people call memory RAM, random access memory? The reason people do that is to be compared with data access on disk, which I'm going to talk about in the next slide. Then I will come back and explain to you why we call memory random access memory. So speaking of that from the database point of view, inside the database kernel, you're going to have a query optimization and execution module, which means take user query as input, pass that into a query plan that the database engine can understand, optimize that query plan and execute. That component we're not going to talk about in enterprise database class. But just keep in mind there is something like that inside the database kernel that will optimize the query plan and execute the optimized plan for you. Then, of course, a related question is how do you represent a query plan? A query plan is always represented by what we call relational operators. Essentially, the relational algebra operators you have studied in the earlier part of this course. Okay? So SQL input will be converted to a query plan represented by relational algebra operators. Okay? And once you have a query plan, you have to execute that query plan using what we call files and access method, which we will be discussing in today, either today or Monday's lecture, briefly into details. Basically, how do you execute this efficiently using certain structures and machineries built inside the database kernel to speed up your query execution. And then finally, no matter what you do in your query plan, you have to, at the end of the day, retrieve data from disk, because database store data on disk. Database do not, by default, database does not store your data in main memory, because if you do that, once you lose power, you will lose all your data in your database. So data is stored in some permanent storage media, like hard disk. However, if you know just a little bit about CPU, about computer architecture, you know CPU, the processors in a computer cannot operate data on disk. They can only operate over data in data cache inside the processor. Does that make sense? So then you have this gap, because data is on disk, but whatever you do, the operation you do has to be over data in cache. This means that you have to do some data transfer between different storage medias. Meaning you have to transfer data from disk to memory, then memory to cache, so that your CPU can operate on this data. Does that make sense? This brings up the challenge of what data you want to transfer, because your cache size is much smaller than your memory size, which in turn is much smaller than your disk size. Which means the naive solution of reading everything into cache is not possible. So you have to be careful and smart about what data to bring all the way from disk to memory, then to cache. Yes or no? Okay? And that particular module who is in charge of transferring data from disk to main memory is what we call the buffer management module inside the database kernel, which we will talk about that briefly. And then how do you lay out data on disk? And this matters, right? For example, when you have a population database, do you lay out data where each record is an individual, right? A student, for example. Do you lay out them to disk by state or by major? That's a decision you have to make. By state meaning records from Utah first, followed by all records from Washington, followed by all records from Colorado, so on and so forth. That's one way of laying out records to disk. Another way is to store all CS students first. Doesn't matter whether they're from Utah or Colorado or whatever. Then lay out students from ECE, lay out students from history, and so on and so forth, by major. Does that make sense? So how do you make such decisions? That's in charge by the space manager. One critical observation you can have here, obviously, is you only have one physical copy of your data laid out in one particular manner. You cannot claim I can have both records by state, then records by major. Of course, you can do that, but then your storage cost is doubled. You may argue my disk space is cheaper today. I don't care about that anymore. But then if you have updates, you have to update 2 copies, or 3 copies, or multiple copies. And that dramatically increases your update cost. And the more copies you have, the more duplicates you have. The more duplicates you have, remember, duplicate is the evil of database system. You will suffer from all these anomalies we talked about earlier. Does that make sense? So it's not a trivial decision to say, oh, I'm simply gonna duplicate my data this many times, and where in each duplicate copy I'm gonna store in a particular format, so that answering this type of query is more efficient. It's not a simple solution like that. Okay? So that's some overview. But in order to understand disk space manager and buffer manager, we have to understand some basics, which is how data is stored on disk and how data is transferred from disk to main memory. If you think about data on disk, there are many different operations you can do over such data. But from the disk space manager point of view, they boil down to 2 abstract operations: read and write. Read and write. Read a particular block of data, write a particular block of data. The particular semantics of your read and write, from the disk space manager point of view, I don't really care. Does that make sense? I only care you ask me to write this block of data, this from Utah, or could be history major from Colorado. Those are what I mean by semantics of the data. From the disk space manager point of view, I don't care. That's something the higher level application should worry about. At the end of the day, you give me a block of data to write to this location on disk. That's all I care. Does that make sense? So from the abstract point of view, database, the disk space manager only care about read and write. The specific semantics of your read and write, disk space manager doesn't really care. It's really the higher level application code need to worry about the semantics of read and write. Does that make sense? So that's what's going on here. So why not we store everything in memory? I have argued about this already. It's very costly if you choose to do that. The type of data we have nowadays, let me show you some database we have in our research group. So you look at this data, we have Twitter data. If you read this value, that's about 3 terabytes of data. If you tell me you store terabytes in main memory, and it's growing, by the way. Our data set grow about 10, 20 gigabytes per day. So if you tell me to store this in main memory, I have to buy a main memory of about at least 5 or 6 terabytes, more than the size of my data, because the size of data is just raw data. If you store that in your main memory, you have to reserve some additional space for manipulation over such data, and for your operating system, and so on and so forth. And that will cost you a fortune. I'm not willing to pay that much money. Okay? So it's very expensive. So you may wonder how we did it, right? But in order to understand this, we need to understand some basics. Back to the basics. So we use this storage hierarchy to address this challenge, meaning I'm going to store this 3 terabytes or 4 terabytes data on disk, and only bring in necessary data to my main memory, which is much smaller in size, for data that I need for the current computation. My computation might change over time, meaning the type of data or the specific content of the data for the current computation may change over time, but I will basically kick out the old data and bring in new data. So that's kind of the high-level intuition behind the proposed approach. The question is, can you do something that's smart to minimize this cost of bringing in data and kicking out data and so on and so forth? Does it make sense? Right? So that's essentially what we're going to do next. In order to do that, we need to understand disk. Disk, another name for disk is hard drive. Most of your computers have something like a disk. The newer machines may not have anymore. They have a disk that's based on solid state drive, like flash. Right? So I'm going to talk about, for now, we assume that we're using magnetic disk, the traditional hard drive. And I will have a brief discussion on solid state drive towards the end of this discussion. Okay? So for now, we'll assume whenever we say disk, we are talking about magnetic disk. That at least half of your computers, the laptop you're using now, are still based on a magnetic disk. If it's not on your laptop, on our servers, when you have terabytes of data, I think 99% you are still using a hard drive for that. You are not going to use a flash drive for it, because flash drive is still very expensive. Okay. So this is a quick overview of hard drive, what it looks like. So hard drive has, in the center, has a spindle. That's mechanical spindle, like metal-built spindle that rotates all the time. Attached to the spindle, you have a number of platters. So each of this is a platter. The platter typically is double surfaced. So you have surface on top and surface at bottom. Both surfaces are magnetic fields that can be used to encode 0 and 1. North is, for example, 0. Magnetic field south is 1. Does that make sense? And this explains why this is permanent, is non-volatile, because magnetic field exists even if you lose power. It doesn't depend on power to store magnetic field. Does that make sense? Right? You should know this, right? The magnetic, whatever my daughter is playing with, she doesn't need to power it to attract metal to it, right? It works all the time. So it's power independent. That explains why hard drive is non-volatile. Okay? Now to look at the structure of the platter take a closer look at the platter. Each surface on your platter will have multiple tracks. A track on a platter surface is all the sectors that have the same radius to the center of your disk, to the spindle. So each of the small white rectangle here is what we call a sector. Multiple sectors with the same radius to the center called a track. So this is one track. Does that make sense? You may wonder, what is a sector? Sector is the smallest unit on a disk to store data. And typically, the typical value for a sector is about 512 bytes. 512 bytes. Meaning, if you write a disk driver, if you write a hard disk driver, whenever you try to read data or write data to disk, the smallest unit you can operate on is 512 bytes. Meaning, a single byte, you have to fetch at least 512 bytes. 512 bytes, meaning at least a sector. Does that make sense? But that's if you write a disk-based disk driver. Right? Oftentimes, we as application developers, we don't have to worry about such low-level drivers. Disk manufacturers oftentimes have such disk driver written for you already. So from the database kernel point of view, I don't have to operate at this low level. So database has a higher granularity in something called block. Does that make sense? A block or page, these are interchangeable concepts, meaning they refer to the same thing. Okay, when I say a block or a page. A block or a page refers to a collection of contiguous sectors on your disk. A collection of continuous sectors on your disk surface. And typical size for a block or page is, let's say, 4 kilobytes or 8 kilobytes. 8 sectors, and this means just 16 sectors. Does that make sense? Of course, they are contiguous. Follow me? So far, so good? So when database operates on your data, like I said earlier, the database manager has two abstract operations, read and write. Furthermore, this read and write are always done in the unit of block. One read is one block read. One write is one block write. That being said, there is another concept called cylinder. We need to define this because when you say database read n blocks or 10 blocks or 20 blocks from disk, what happens if you have finished all blocks, meaning all sectors, from the same track? What do? Do you go to the next track on the same surface, or you go to the next track down to the next platter? Does that make sense? You go this way or this way. So far so good? This brings up the concept of cylinder. It's an abstract concept on disk. A cylinder is nothing else but all the tracks from all platters up and down surface, right? Remember that each platter has two surfaces. A cylinder is all the tracks from all the platters, both surfaces, with the same radius to the spindle. So that forms a cylinder. Does that make sense? And the concept, what do we mean by next block or next page? Refers to, here is critical, okay? Next block from the same track, and when you have finished all the blocks in the same track, next block becomes the next block from the next track in the same cylinder. When you have finished all the blocks from all tracks in the same cylinder, what do? Of the next cylinder, you increase the radius a little bit. So that's the order of blocks on disk in the eye of database system. So it's like this. Then expand. Go down again, come back, go out. So far so good? You may wonder why. Why we do this. We have this arm assembly. This is a mechanical with arms attached to the assembly. So this is called the assembly. These are what we call the arms. And you have multiple arms, 2 arms per platter. Why 2 arms? Because for upper and lower surface. And you have multiple arms, such arms, every 2 arms per platter. So you have 10 platters, you will have 20 arms. Does that make sense? Up and down for each platter. The way you read data from disk to main memory is as follows. The arm assembly of each arm, you're going to have a special field, special thing. That's that black rectangle there. What that black rectangle is able to do is to convert magnetic field into electrons, into electronic signals, meaning positively charged signal and negatively charged signal. Why you do that? Well, you convert magnetic field from south and north to positive and negative electron signals. That means 0 and 1, convert 0 and 1 from this, something that computer can now understand. And it's so far so good? So that's how you read data from disk. Now you guys should know about this, okay? With that being said, let's come back to the concept of block, how exactly this thing works. Higher level application code will tell the database system, I want this data, which translates to some location on your disk. I want the 100th page on disk. And then there is a location translator inside the disk space matter. 100th block locates at this particular location on disk. Okay? And that will be converted to an instruction to the ARM assembly so that the ARM assembly only moves in and out, doesn't do anything else, only move in and out. And the disk letters rotate all the time, clockwise, like this. So the system like this. This thing move all the time, rotate all the time, and this ARM assembly move in and out. With the combination of the two, you can tell the head of the ARM can do any location on your disk in this three-dimensional space. Any question on that? With the combination of in and out and the rotation, the head of the ARM can be aligned to arbitrary location on your disk in this 3D space, the three-dimensional space. Follow me so far? So how do you do it? Well, if you tell me the 100th block is in the second cylinder, first track of the second cylinder, and starting at 100th sector on that track. How do I do it? Well, I will move my arm either in and out, depending on the current position of the head of the arm, so that the head of the arm is aligned with the second cylinder, meaning with the right radius. You have one cylinder, two cylinder, third cylinder, so on and so forth. So I will move my arm in and out, depending on my current location, so that it's aligned, the head of the arm is aligned with the second cylinder. But that's not enough, because the 100th block starts at, let's say, the 100th sector on that cylinder, on that first track. And I know it's the first track, so I will activate only the first arm among all the arms in the cylinder that I'm going to read data from. But that's not enough, because the sector might not be aligned with the head of the arm yet. It could be here, but that's okay, because this thing keeps rotating. Eventually, it will rotate right beneath the head of my arm, and when that happens, I will start converting the signals, magnetic to electron signals. That continues, if I'm reading only one block, that continues for 8 sectors. If my block size is 4 kilobytes, sector size is 5 bytes. So I will wait for the rotation of 8 sectors, then I'm done. Then that's one block of data converted from disk to memory. Quick.
How fast does this all happen? It all sounds extremely complicated, yet I don't notice any time difference. So how fast is this?
What's your question again?
How fast is all of this operation done?
Well, of course, this is slow, but how the plane flies, mechanical works, right? So, yes, I'm doing this extremely slow, but I will take the other question offline. If you have a question, come to my office, because I really want to move forward with this. Okay. Now, actually, the next thing I'm going to discuss is back to Curtis' question, how fast this thing can do, right? There is a limitation. What limitation? The in and out, this ARM assembly is controlled by mechanical structures. But inside computer, we know 1 and 0 are represented by positive and negatively charged electrons. What's the speed of electron, by the way? How fast electron can move? You know, some basic physics.
Electrons, if I remember right, the field might move fast, but the actual movement of electrons is very slow.
Let me put it this way. How fast can you transfer electricity? How fast can you transfer electricity? Basic physics.
It depends on the conductor.
Okay, let's assume nearly zero resistance in an ideal environment.
Isn't it like 2 speed of light in copper?
Yes, nearly the speed of the light. Nearly the speed of light. Here it is. Nearly the speed of light. That's how fast this thing can move. However, that's when you have electrons, signal represented by electrons, right? This converter, if you think of this arm assembly is not light. It's not made up by light. It's made up by mechanical structures. How fast can a mechanical structure move? I don't know. Car can move 80 miles per hour. Plane can move, I don't know, 500 miles. Spaceship can travel even faster. But as far as I know, if you know something different, let me know. Any mechanical structure that human can make is much slower than, I don't know anything that can, mechanical structures can move nearly at the speed of light. Does it make sense? Yes or no? Which means the bottleneck of the system, where is the bottleneck of the system? The bottleneck of the system is move in and out of your arm assembly and rotation of your platform. Those are mechanical operations. Those are the bottleneck of your system. Once you convert magnetic field to electron signals, those latency can almost be omitted because the bottleneck is really these two things, in and out and rotation, because those are mechanical movement. Does that make sense? Yes or no? So far so good? This brings up, related to Curtis' question, how fast this thing can move. When you buy a hard drive, there's something called RPM. Have you guys ever paid attention to this parameter when you purchase a computer? Can someone tell me what does it mean? RPM.
How many revolutions per minute the hard drive can do?
Yes. I'll put it in simple language. How fast can hard drive rotate per minute? Rotation per minute. Now you know why this is important. Give you a simple experiment. I move my arm assembly to align with the right cylinder. I know the rate, but data is here. Scenario 1, rotate like this, boom, you can start reading data. Scenario 2, boom, you can start reading. Which is better? Which is better? Come on, it's not rocket science. Second one is better. So, what should you do with RPM? Which has higher RPM? This or this? Huh? Come on.
The first thing you're rotating isn't just going straight?
The rotation, right? Not going straight. These are cylinders, these are the circles, right? Which one has higher RPM? Let me ask this question one more time. This or this? Second one. Okay, RPM. Why? Because if you have X RPM, meaning you can do X rotation per minute, how fast you can rotate? How long does it take for you to do one rotation? How do you do that calculation? It takes for one rotation. Does that make sense? 60 seconds. Right? So the higher this value is, the faster you can rotate. The less time it takes for you to rotate. So now the answer to your question, Curtis. Okay? You want to know how fast this can do? Turn back your computer, look up the configuration of your computer. There must be something called RPM. I'll tell you how fast this thing can rotate. Okay, now skip this. There are three things that dictate how fast you can read and write data from disk. One is called seek time, the other is called rotation delay, the other is called transfer time. We just explained rotation delay, so I will go with that first. Rotation delay basically tells you how fast your platter can rotate. How long does it take to do one rotation? And you calculate that value using RPM. However, if you think about it, in any given random rate you are going to do, what will happen typically? What happens is this is your platter. Suppose this is you have multiple tracks. Yeah, so you have cylinders. I'm going to omit that. Okay. Let's say this is the surface I'm going to read data from, and this is my arm assembly. My arm assembly now is here. This is the head. But the data I'm going to read, the block, is here. Let's say that's 8 sectors that I'm trying to read. So far, so good? When can you start reading? Well, this thing is rotating. Wait until this is under the head to start reading data. You follow me? So there is a delay. The time it takes to go from here to here, that's rotation delay. And what's the value for this? Well, obviously it changes from case to case. You could have a scenario like this. You could also have a scenario where your data is here, or your data is like right here. So your rotation delay might be different. Yes?
Isn't this seek time?
No, this is the rotation delay. I will explain seek time later on. It obviously depends. Do you follow me? So we don't know the exact rotation in each particular case. But how do I make an argument for the average case? What's the average rotation delay if you do enough such rotations, or such rate from this track? If you look at assuming uniform distribution for the starting address of the data you try to read, this could be just below the head of your arm, a little bit further away from the head of your arm, further away from the head of your arm, or really just you have really bad luck. The data you try to read just rotate after you. So you have to wait for a full rotation to come back. So what's the average rotation you expect, roughly? Half rotation you expect to do. That make sense? Uniform distribution starting from just, is going to just come and just pass you. So on average, you need to do half rotation. So what's the rotation delay we use in our calculation? Well, you calculate value, how long it takes to do one rotation, and you divide by 2. Give you the rotation delay of your disk. So far so good? So that's rotation delay. What about seek time? Seek time quantifies the time, the average time it takes to move your arm in and out, to align the head of your arm to the right cylinder. Yes. Again, this is value. Again, this is obviously a value depends on the current location of the head of your arm and the data you're trying to read. So this manufacturer typically will give you this value. If you look at the specification, the text specification, they oftentimes tells you my seek time delay is this much, which is in the average sense. Does it make sense? Finally, there's another component that matters, which is transfer time, which means how fast you can convert one sector of data from magnetic field to electron signals. How fast the head of the arm can do the converting. And this typically is a much smaller value than the rotation of the sector itself. So this is the tricky thing to remember, okay? When I'm trying to convert this sector of data, this is the head of my arm. The head of arm stayed at the same location. This platter is rotating, so this sector of data will slowly, of course, in reality, this is pretty fast. Let me do it in extreme slow motion. What happens is I will rotate like that. And during this process, the head of the arm is busy converted to electrons. Does that make sense? What I'm going to tell you is the speed of that conversion is typically much faster than the rotation itself. Okay? So this data conversion speed is actually dominated in the most part by the rotation time itself. And how do you compute the rotation time for one sector? That's easy. You use the total time, this many rotations, and you know for X rotations how many sectors you have per track. Of course, typically it's a much larger value. Let's say, assuming 100 sectors per track, this means I will do 100x sectors. I will rotate this many sectors in 1 minute. From this, I can derive how many seconds it takes to rotate one sector. That make sense? And then from that, I can calculate how many seconds it takes to rotate one block. So far, so good? So reading one block of data takes the following cost. 6 time plus rotation delay plus time to rotate that one block of data. That's the total cost of reading one block of data. Same as writing one block of data back to disk. If it's not really critical, ask a question during my office hours. Okay? I'm sorry for this because we're running really late behind schedule. That brings up, once you understand what we said so far, that brings up the concept of random access versus sequential access. Random access versus sequential access. You follow me so far? Why there is a difference? Very simple example. I'm going to read 10 blocks of data, 10 pages of data. You know, typically a track is big enough to hold 10 blocks. If you have 4 kilobytes block, 10 block is just 40K bytes. That's equal to 80 sectors. 80 sectors. A track typically will be able to hold that much data, 80 sectors. That's no problem. Let's look at sequential access first. By sequential access, I mean those 10 blocks are next to each other on the same track. You follow me? One block, next block, second block. This is what we call sequential access. Do you follow me? What's the scenario? Okay, we need to pay a 6 time. Unless I'm really lucky, the head of my arm is already aligned with the same track. Typically, it is not. So I move in to this track. Unless I'm extremely lucky, the current sector is the starting address of the first block. Typically, it is not. So I have to pay a rotation delay for the first sector of the first block to be rotated right under the head of my arm. So far, so good? But after that, what happens? Do I need to move the arm anymore? Do I need to move the arm 10 sequential blocks? 1 block, 2 block, 3 block. All I'm doing is wait for those 10 blocks to rotate over. The time for that is simply rotation time for 1 block times 10. That's it. But I no longer pay any 6 time delay and rotation delay except for the first block, but I don't pay any of that for any other blocks I'm going to read. So the more I read, the more benefit I get because I'm paying 1 6 time and 1 rotation delay for these many blocks I'm reading. That's sequential access. What about random access? Can someone tell me what's going on for random access?
The blocks they're going to be in different positions.
Yes, and for that?
So you're going to move the head. You're going to pay seek and rotation every time you read.
Excellent. You need to pay 6 time and rotation delay for every single block you're reading. scenario, okay? Moving here, rotate, boom, one block. Then you have to move again, rotate, third block. Big difference. So sequential and random rate, huge difference. You follow me? You don't trust me, do some experiment on you, write a simple program. Read an array of elements from disk, that's sequential, and read a random location from your disk. You will see a performance difference of at least 10 times, sometimes more than that. The earlier point I was trying to argue today, why we call memory random access memory. Now we're ready to answer this simple question. As computer scientist student, you should be able to answer this. Why memory is called random access memory?
The blocks aren't stored sequentially.
Huh?
Blocks aren't stored sequentially.
Well, not necessarily. I can still store an array of integers sequentially in memory. In fact, you're encouraged to do that. If you write your computer program. Dylan?
So neglecting cache, main
Yeah,
memory,
neglecting
it's
cache.
pretty much equal cost. Like the cost to access your main memory doesn't depend on where you, like what you last read.
Yes.
It's constant.
The cost of reading one unit, this unit can be defined in your architecture. Typically, I don't know. I mean, it's depending on your block size or page size in your main memory, right? The cost of reading one unit of data, if you're reading from main memory, is independent of the location of your data. In other words, the cost of sequential access 10 blocks in main memory is almost the same as randomly accessing 10 blocks in main memory. And this is hugely different from disk we just talked about. The cost of reading 10 blocks sequentially is much cheaper than reading 10 blocks randomly on disk. But for memory, literally almost no difference. Why? Why is that? Why is that? Why is that in memory? Because data in memory are stored by electrons and travel almost in the speed of light. Of course, there are other reasons, but high-level rationale, that's the reason why. When you have speed of light, humans cannot detect such latency. Human system cannot detect such latency in such short distance, of course. Your memory chip is like this big. If you store your memory as big as universe, then random and sequential access, you will see a difference. You read 10 blocks from Moon versus read 10 blocks from Mars and galaxy, big difference. When we squeeze the universe to as small as we matter, reading data from Moon is the same as reading data from Mars, the Moon, and Sun, doesn't matter. Make sense? When you travel at the speed of light. And that's why memory is called, to highlight that distinct property, people name memory as random access memory. Because that's critical. That's a critical feature that your memory is able to provide to you that disk cannot provide that for you. Yes or no? Okay? So there's some calculations, you can read this yourself, but that's pretty much what I said so far. Concept next block. I said earlier, when I read data sequentially, I need to define what you mean by next. The first block, next block, next block. Here is the definition. Next block refers to the next block from the same track. Once you finish all the blocks from the same track, the next block from the next track in the same cylinder. When you have exhausted all tracks from the same cylinder, next block becomes the next block from the first track of the next cylinder, so on and so forth. The reason now you understand why people define like this, because if you go this way, when you jump from track to track, you do not pay 6 time delay. You only pay another rotation time delay. You only pay a 6 time delay when you have exhausted all tracks from the same cylinder, and if you're still trying to read the next block, only then my arm needs to move, and the movement is the smallest possible, which is to move to the next cylinder. That's the smallest possible distance you can expect. for the arm to travel. That's why we design. That's why people define next like this way rather than this way. Because if you this way, after finishing every track, you need to pay a 6-time delay. Much more expensive than this way. So there's a reason for that. Okay. So some examples, but I'm gonna show you an experiment in our research. In our research, we did something like this. Okay. A DD is a daemon, a person. You can understand DD as a user program that's running, and DD is a sequential access client. So it sequentially read data from disk. And what this picture tells you is, this is the time, and this is the location I'm reading from. And it's represented by, encoded by offset to some initial location value. Does that make sense? And the lines are formed by many, many dots. Each dot represents the location in the offset value that I'm reading from at that particular time. So at this time, I'm reading from this location. At this time, I'm reading from this location. So this curve clearly represents a what? Sequential read workload. My offset increase nicely and linearly over time. So I'm reading the next offset value all the time. So I'm this way. Does that make sense? And occasionally, I do some random jump. So from here to here, that's a random access. But I only do random access every so often. So for the most part, it's a sequential access. Okay? So you may wonder how we get this measurement. Well, it's not really. We modify the D-space driver and all that and to get this measurement. Okay? So far good? Yes or no? Each dot represents one I/O. Input and output of one block. So each dot represents I'm reading one block. I'm not going to answer a question for this because I have to take question off. And this is the research related stuff. Okay. Now I'm going to keep doing the same workload. Here is where the experiment becomes interesting. Okay? I'm going to keep the same workload, but computers do not have only one workload running at the same time. You may be doing sequential access. Another person may come in and do random access. Does that make sense? So, sequential client. RR is another workload by another client, and this client does random read. You can see this is pretty much random. Does that make sense? Yes or no? You can tell disk space manager can still pretty much preserve that sequential access while serving the other random access. That's if you have only one random access workload running concurrently with your sequential access workload. Does that make sense? Yes or no? Can you tell the sequential workload anymore? Yes or no? No, you cannot. What happened? Here in this experiment, I'm running that one sequential workload, and I'm running that two random read workloads. I duplicate that random read client. As you can tell, the default disk space manager fails in the sense that it totally destroys the sequential workload. Why? Because to be fair, the disk space manager cannot serve that sequential workload first, then serve that random workload. What the disk space manager has to do typically is to interleave, kind of like transactions. Interleave the action from that sequential workload and those two random workloads. If you add enough random workload, the arm will move in and out. That sequential workload is no longer sequential. Does that make sense? You may wonder why this matters. Well, if you use Amazon.com, Amazon Cloud Service, how many of you use Amazon.com? Others from Microsoft for your product development, I noticed. That's a cloud service, right? You rent some virtual resources from there, and they charge you based on the time you run your workload, right? I can easily make you pay much more than what you're supposed to pay. Suppose you have a sequential workload running, and I know which virtual machine server you are using. I simply request to be co-located with you and start running some random workload. then your running time of your job will grow from 10 seconds to 10 minutes. Then instead of paying 10 seconds of money, you pay money. Without doing anything else. That's all I need to do to make you pay more than what you have to pay. Does that make sense? Yes or no? So, bottom line, don't let me know which virtual machines you are using. If you let me know and you did something bad, I can easily make you pay a little bit more. Very simple. I just want some random workload. That's it. With 4 random rate running concurrently with sequential, you cannot tell at all. You may wonder what's the big deal. I cannot tell. Let's look at the bandwidth. Throughput. How many blocks you can read per second for each workload. The blue curve represents sequential workload running by itself. The green curve represents sequential workload running with 1 random rate workload. As you can tell, adding 1 random workload decreases the bandwidth of your sequential load, but not too much. But once I add 2 random rate workload, look at the bandwidth. It's almost a 10 times drop, 6, 7 times drop. Meaning, if Amazon charges you by time, you pay pretty much. We're reading the same amount of data, nothing else. Nothing else changed. Okay? So deep space manager is, I hope I convince you, important. And it's non-trivial. That's all I'm going to say about this module. If you want to know more, we just don't have time for it. Okay? But this is an important module to know. Okay? Next, buffer manager. Like I said, data resides. And in order for your system to operate over your data, you need to bring that data from disk to buffer, in other words, to your main memory, and transfer your data from main memory to cache. The latter transfer, meaning transfer data from main memory to cache, I will ignore. Because typically, if you talk about a D-space database management system, the bottleneck of data transfer really is to transfer data from disk to main memory, and the transfer cost of data from memory to cache is typically dominated by the transfer cost from disk to memory. So I will focus on this part, but increasingly, a lot of database systems focus on main memory database system, meaning for the most part, my data is in my main memory. In that case, you have to consider the transfer cost between memory to cache, because that becomes dominated. Because you no longer have many transfer from disk to memory. Okay? But for the purpose of this class, we focus on disk-based database system, which is still the majority out there. So we focus on transfer operation from disk to memory. Okay? For that matter, database system will have something called buffer manager. We will have something called buffer manager. And this is a buffer manager. A buffer manager is nothing else but a module that manages a collection of memory space in your main memory. Remember, if you have, let's say you have 8 gigabytes of RAM, you're not going to use all 8 gigabytes for your database server, right? Because you have operating system, you have other. So typically you will allocate maybe out of that 8 gigabytes of RAM, you allocate 2 gigabytes or 4 gigabytes of RAM to your database. That 2 gigabytes or 4 gigabytes of space allocated by your system to your database is managed by buffer manager. And that 2 gigabytes and 4 gigabytes of space become what we call the buffer. So far so good? And conceptually, because database system operates in the unit of block or page, we partition this buffer into a collection of pages or collection of buffer. So a collection of blocks. Sorry. So of this rectangular box represents a page or a block. That make sense? And a white rectangular box represents a free block or page in your buffer, meaning that buffer in your memory is available to use. Nobody is currently residing in that particular page or block. A black square box represents an occupied block or page in a buffer. Does that make sense? Now, how this works? So this is your buffer, and has many pages or blocks. Okay? And this is your disk. Suppose your data is like this part of your disk. And this obviously is much, much bigger than the size of your buffer. Terabytes versus 2 or 4 gigabytes. So far so good? Some higher level process will say, get page 10. And that process will send this request to the buffer manager. The buffer manager will look up this page 10 in the buffer. If it's there, I will return this request to you immediately without visiting the disk, which is good news, because visiting disk is expensive, as we explained just now. But if it's not there, would I have to go and fetch page 10 somewhere on disk? A copy of that data, how do you do that? You pay the seek time delay, rotation delay, and wait for that one block to rotate over, read the data, convert it to electron signals. That become a one-page data in your buffer with the exact same content. And that will be placed into your buffer. Where do you place this into? Well, it doesn't matter. As long as you have at least one available buffer frame. This is the terminology we use. Each of this page or block in buffer is called a buffer frame. So I will take this page and place into a available. You follow me? So that's complete one cycle. Then I will tell you to get data from this buffer frame. So CPU will then fetch this from here to cache and go on. So far so good? Yes or no? Now, CPU may come back with the first one. I say get page 20. I will ask for it, not there. I will go, get 20, get back. It's 10, it's fine. I serve this request back. For the third time, I come back and say, get me page 10 again. Now things are slightly different. What happens? How do you serve this request? Do you need to go back to disk for this? No. No, you don't need to. Of course, you still can. Be my guest if you do that. Your company will go bankrupt in probably 2 days if you do that. Because others will not do that. And they will 10 times than your database system. Nobody going to pay and buy your system. They will go and fetch this and return without waiting back to the disk. Much, much, much faster because you no longer pay this and that. You get from memory right away. You follow me? This motivates a very interesting observation, which is once you have fetched some page from disk to main memory, after serving that request, you do not want to throw in some sense free the buffer frame right away, because this goes back to my earlier response to I think his question. You want to maximize the locality of your program. Locality of your program means that if you have access something just now, you want to cluster the access to the same thing together, or cluster access to the nearby items together. Now you understand why we need to maximize the locality of your program. Why? Because that increases the buffer hit rate. of your system. So your performance gets much better. The same phenomena is copied into that transfer from memory to cache. Your data cache has locality too for the same reason. So locality is important at both levels for this reason. Yes or no? Now, of course, if we continue this game, eventually you may end up like this. Draw less number of blocks next time. Anyway, you end up with this. That's possible, right? After a sequence of these requests. Yes or no? Follow me? Now I ask for nth request. I ask for get page. Whatever. That's 976. And there, then fine, you serve the request. But if it's not there, what do? Well, you say I go back to disk. I find 976. But then you face a question: where do I place this page into my buffer? My buffer is fully occupied. Yes or no? That's the question. Okay? And that's essentially the job of buffer manager, which is to figure out when your buffer frames are all occupied, which frame you use to store the next page request. And there are many replacement policies. I'm going to talk about a few very intuitive ones. RRU, MRU, clock, but I will focus on RRU. Least recently used. And the name is self-explaining, right? What do I mean by least recently used? Among all the frames that all of them are occupied, I will choose one of them to kick out the buffer, kick out the page there, and place this new page into that frame. And I need to decide which one to kick out. My decision is based on who is least recently accessed. I look at the request history. So this was accessed in the last request, and this was accessed, the most recent access to this was 1,000 requests ago. And that's the furthest back in history among all the frames. Then I will choose you to replace least recently used. Does that make sense? Similarly, you can define most recently used. You may argue, what's the intuition? Well, least recent use is very intuitive, right? You haven't been accessed for a long, long time. The probability somebody will come and access you in the near future is low. So I should replace you. But you can similarly make an argument that if something has not been accessed for a long, long time, likely somebody will access that. If Utah Jazz hasn't been into playoff for 10, 20 years, maybe next season is the season. The hype will build up. The more years they're not going to make it to the playoff. Yes or no? But somebody can argue, come on, Utah Jazz hasn't been into playoff for like, what, 20 years? They're not going to be into playoff. Throw them away. So you can make argument both ways. Least recent use, most recent use. You can also make argument based on the of the access. Frame 1 hosts a page that has been accessed 1,000 times. Frame 2 hosts a page that has been accessed only 5 times. Let's say in the most 10,000 requests. Which one you are willing to bet on for the next request? Huh? What's your bet? Hypothesis bet. Okay, you don't have to bet money on this. Okay?
Most popular one.
Typically, people will go, oh, that has been accessed 1,000 times out of 10,000 times. This has been accessed only 5 times. If you ask me to bet, I probably bet the 1,000 times once. And this, of course, that means you will kick out the one with least frequently accessed. Right? So that's what we call most frequently used or least frequently used. You can define all these arguments. Define all these different replacement policies. Here comes the interesting aspect of all these policies. No one is the winner in practice. They are all actually, surprisingly, from a theoretical point of view, roughly the same. If you assume all possible inputs, activate some strong characteristics that favor certain type of replacement policy. But if you assume random access sequence, all of them roughly behave the same. And there is something called competitive ratio that quantifies this from theoretical point of view. I want to show you one example where least recent used is not very good. Okay? Least recent used very good. I'm going to show you one example. This actually is the worst thing you can do, policies. Okay? How do I do that? Let's look at this together. Very simple. Let's say I have 5 frames in my buffer. Okay? 5 frames. Initially, of course, they are empty. Okay? And you know what? You only have 6 blocks of data on disk. Cannot be simpler than this. 6 blocks of data on disk that you care. The disk might have terabytes, but only 6 blocks I care. Next time I'm going to say 3 and 4. 6 is too much. Anyway, 6 blocks of data on disk. Which means your request will be one of the 6 at any given time. And I'm a simple person. I want to simplify this all the way down. I'm going to do sequential access to these 6. 1 to 6. 1 to 6. That's what I do. You may wonder why do you do that. I don't know. I want to check whether these people are doing their jobs. Sequentially, I check them. Do you do your job? Do you do your job? Do you do your job? And come back. Do you do your job? Do you do your job? So on and so forth. You cannot be simpler than this, right? What happens? Let's look at what happens. Suppose I'm using RRU. Least recently used. Okay? What happens? When I request 1, I get it in. That's I/O to the disk. When I request 2, 3, 4. The first 5 requests are simple, right? 1, 2, 3, 4, 5. All these 5 requests will be served with one disk I/O operation because there are nothing in the buffer to begin with. Yes or no? Now, here comes like magic, interesting part. And next request is 1. And what happens to 6? Do you have space? Do not have space. So you have to kick out 1. Which one you kick out? 1. If you're using least recent use, you kick out 1. Kick out 1, right? So this becomes 6. Feel pretty good about it. Until see the next one, which is what happened? I don't know about you. If it's me, I was like, what the heck? I just replaced the one I'm going to access. I should have saved one disk I/O, but now I have to kick out 2. Do you see the pattern now? Yes or no? You are replacing, you are doing the worst possible thing. You are always replacing the next guy to request. You increase your cost almost always by 1 in each single request. What's the best policy here? Can someone tell me? Yes, if you go with most recent use, what happened? Let's rewind history. In practice, keep in mind, you cannot replay history. If you didn't start working on 5th grade, you didn't start. You cannot go back and say, I want to start early. No way. So you only have one chance. But let's say it's a computer game. You can save and load. I do that all the time when I want to play. Okay? You can save and load and try a different strategy. So most recent use. Now, 1, 2, 3, 4, 5, it's the same. When it comes to 6, which one I should replace? Which one I should replace? 5. When it comes to 1, what do? Do I need to pay a pace? No, 1 is here. 2 here, 3 here, 5 here. 4 here. Until I request the next 5, I need to do another replacement. Much better. But then you argue that I should always use most recent use. But as soon as you make that decision, I, as an adversary, I change my request. Okay, you tell me you're going to use most recent use, right? Fine, I'm going to do 1, 2, 3, 4, 5, 6. Not 1, 2, 3, 4, 5, 6. I will do 5, 4, 6, 5, 3, 2, 1. The worst possible policies. And this is what we call in computer science an online game. Means both parties may change the behavior of what they do depending on the move of the other party. Pretty much like playing a chess. You follow me? And what's the best strategy? Well, that's obviously a deep question. Google just built AlphaGo to beat, this is the most sophisticated human chess, by Chinese. That's the most sophisticated human chess game that you can imagine. And Google just built a game, a system called AlphaGo that can beat human players for the first time in history. So to answer this question goes beyond what I can do in this class. That deserves a course by itself. But just keeping this in mind, this is not a trivial question. Don't pack up yet. I have 2 minutes. Okay? So that shows you the problem. And the slide there, this concept called pin and unpin and so on and so forth. Ignore those details. I decided to skip all those because pin and unpin, so far, we assume read-only access. Meaning you read those buffers, you read those pages, you bring those pages back to the buffer, but you never do any updates to the buffer frames. In practice, not only you need to read data, you may do some computation and update the data. For example, for all students from Utah, give them 10% boost on GPA, 1.1 times their GPA if it's from Utah. To answer that, to do that, you will read all the pages with to buffer, update all the values, and at the end of the day, what do you need to do? When transaction commit, you need to write those updates back to disk to make those changes permanent on disk. This brings up another interesting challenge, which is when you replace buffer frame, if the buffer frame has been updated since the last time it has been read to the buffer, you cannot simply do a replacement. You have to write a dirty frame, quote unquote dirty, meaning things have changed, back to disk before you can do the replacement. That pin is for that purpose. You can ignore that. I don't require you to understand all this detail. Furthermore, if you think about the transaction requirement, ACID property, I hope you still remember what ACID means. Durability says once transaction commit, no matter what happens, all the changes must be permanently reflect on your disk. Easy to say, very difficult to do. Because changes are made in buffer. If you lose power to your system, what happens? All the changes you have made are lost forever. You no longer satisfy ACID properties. For you translate, computer doesn't operate on disk data directly. Computer never operates on permanent data directly. So how do you ensure ACID property for transactions? Well, your data is in main memory, and you're doing all this busy replacement, and magically, once I commit, even if your system fails, I can still recover all the changes you have made. And suppose you have some magic way of doing that, during your recovery process, meaning system crashed, in the recovery process itself, system may crash once more. Remember that movie called Inception? You may be in a dream of another dream. You may be in the recovery of another recovery process. How do you figure all this out? So if you think anywhere data class is hard, think about those problems. Okay? So that's buffer management. Okay, I have to stop here. So let me tell you this. I don't think I have enough as what I would like. So the due date of the written assignment 5 will be not on Monday. I don't think I can ask you to do it, but I will release homework 5 regardless. And you can start working on the part that you can work on, such as transactions, basic understanding of disk and buffers. And I will use Monday's lecture to cover a little bit more and tell you the exact due date of written assignment 5. But you should start working on written 5 right away. I will release that today. Okay?